Okay, so our third type of matrix is orthogonal matrix. So the definition of this orthogonal matrix is a square matrix is called orthogonal matrix if A into A transpose, we have any matrix A transpose is the transpose of the matrix. Now if I multiply these two matrices and if I get identity matrix, then in that case this matrix A is called orthogonal matrix. So a square matrix A is called orthogonal matrix if A into A transpose is identity matrix. Now there are two very important results related with this orthogonal matrix. The first one is if you calculate the determinant of any orthogonal matrix, then either you will get +1 or -1. So this is first property, and this you can easily prove. If A is any orthogonal matrix, then we know that A into A transpose, this will be identity. If I take determinant on both sides, then I will get determinant of A into A transpose, determinant of identity. Now this I can write as determinant of A into determinant of A transpose. Determinant of identity is 1. So this means determinant of A, and we know that determinant of A transpose is same as determinant of A. So I can write this as determinant of A square is 1, which means determinant of matrix A, this will be +-1. So in case of orthogonal matrix, the determinant will be either +1 or -1. So this is first property. And the second one is, and this is very important property, in case of orthogonal matrix, inverse of the matrix is simply the transpose of the matrix. So this is very, very important result. In GATE also questions were asked on this concept. So see, inverse is, suppose if I have two matrices A and B, and if the product of these two matrices is identity matrix, then in that case we say that B is inverse of A and A is inverse of B. If the product of two matrices is identity matrix, then it means each matrix is the inverse of other one. Now here we have two matrices A and A transpose, and their product is identity. So I can say that the second matrix A transpose is the inverse of matrix A. So this is very, very important result. The moment we know that a matrix is orthogonal matrix, we don't have to calculate the inverse. The inverse will be simply the transpose of the matrix. So these are two important results related with orthogonal matrix. Now there was a question in GATE 2018 based on this orthogonal matrix. A matrix Q was given, and it was given that Q is orthogonal matrix. The question was we had to find the inverse of this matrix, and 4 options were given. I'm not writing the option, but those 4 options were given. Now the question was, which of these following 4 options is the inverse of this matrix Q? Now since it is given that the matrix is orthogonal matrix, we don't have to calculate the inverse. The inverse of this matrix Q will be the simply the transpose of the matrix. Now if you want to take the transpose of this matrix, the transpose will be 1/7 is outside. The first row is 3, 2, 6, so this will become first column. The second row is -6, 3, 2, so this will become the second column. And the third row 2, 6, -3, this will be the third column, 2, 6, -3. So this will be the inverse of matrix Q. So this was very simple problem. Only thing that you had to know was that in case of orthogonal matrix, inverse is simply the transpose of the matrix. So these were first 3 types: symmetric, skew-symmetric, and orthogonal. Now after this we'll talk about Hermitian, skew-Hermitian, and unitary matrix. Okay, so our next concept is conjugate of a matrix. Now before understanding this concept, we have to learn what is conjugate of any complex number. So suppose if Z is the complex number, say Z is x plus iota y, then iota is root over -1. So x is the real part of this complex number and y is called imaginary part of this complex number. Now conjugate of this matrix is nothing but a matrix obtained by changing the sign of imaginary part. If Z is x plus iota y, then Z conjugate will be x minus iota y. So suppose if I have a matrix Z as say 2 plus 3 iota, so this means the conjugate of this matrix, this will be simply 2 minus 3 iota. So that is the idea of this conjugate. Simply change the sign of imaginary part and then you will get the conjugate of the complex number. Now we have to learn how to find conjugate of any matrix. So suppose if I have a matrix A and say the matrix is, the first row is 2 plus 3 iota, -2 minus iota. Here I have say 4 iota and this element is say 2. So suppose if this is the matrix that we have and we have to find the conjugate of this matrix. So conjugate of this matrix will be represented by A bar, and this will mean that we have to take conjugate of each of these 4 elements. A matrix obtained by taking conjugate of each of these elements is called conjugate of the matrix. So if I take the conjugate of this element 2 plus 3 iota, then conjugate will be 2 minus 3 iota. Similarly, conjugate of minus 2 minus iota, this will be minus 2 plus iota. Conjugate of 4 iota, this will be minus 4 iota. And since 2 is real, I can write this as 2 plus 0 iota. So conjugate will be 2 minus 0 iota, which is nothing but 2. Conjugate of any real number is the same number. So this matrix is the conjugate of matrix A. So that is the idea of this conjugate of a matrix. If you take the conjugate of each of the elements, then you will get the conjugate of matrix. Now next concept is transpose conjugate of a matrix. So next is transpose conjugate of a matrix. Now as it is obvious from the name, we have to do both of these operations. We have to take conjugate and we also have to take transpose. So suppose if this is my matrix A, and if I want to take the transpose conjugate of this matrix, so first we have to take conjugate and then we have to take transpose of this matrix. You can also do this in reverse manner. First you can calculate the transpose and then you can take the conjugate of the matrix. You will get the same result. And these two operations simultaneously is represented by a to the power theta. A to the power theta means you have to do both of these operations. You have to take conjugate and you have to do the transpose of the matrix. So suppose if this was our matrix A and the question was we had to find the transpose conjugate of this matrix. So first step is you have to find the conjugate of the matrix and then you have to take the transpose of this matrix. So if I take the transpose of this matrix, then our first row will become first column. So first row is 2 minus 3 iota minus 2 plus 3 iota. So this will be 2 minus 3 iota minus 2 plus iota. Then second row will become second column. So minus 2 plus 4. So this matrix is nothing but transpose conjugate of matrix A. First we have taken transpose, then we have taken conjugate. Now there are some. Now the next two type of matrices, Hermitian and Skew-Hermitian matrices, are based on the concept of transpose conjugate of matrix. So next we are going to talk about Hermitian and Skew-Hermitian matrix. So our fourth type is Hermitian matrix. Fourth one is Hermitian matrix. So the definition of Hermitian matrix is a square matrix is called Hermitian matrix. Hermitian matrix if conjugate transpose of A, this means A to the power theta, is same as matrix A. If conjugate transpose of matrix A is same as matrix A, then in that case we say that matrix A is Hermitian matrix. Now obviously this is basic definition of Hermitian matrix. We are going to see what is the second definition of this Hermitian matrix. So suppose if I have a matrix A and say the elements are x1 plus iota y1, x2 plus iota y2, x3 plus iota y3, x4 plus iota y4. I am taking an example of 2 cross 2 matrix just to explain the second definition of this Hermitian matrix. So now if this is my matrix A, then conjugate transpose of this matrix will be, first we have to take conjugate of each of these elements. So this minus sign, this plus sign will change into minus, and then we have to do the transpose of the matrix. So you can easily see that conjugate transpose of this matrix will be x1 minus iota y1. This element will be x2 minus iota y2, and then we have to take transpose. So I will get this element here. Similarly, our second column will be x3 minus iota y3, x4 minus iota y4. So this matrix is nothing but conjugate transpose of matrix A. Now the question is, if A is Hermitian matrix, then conjugate transpose of A, this will be equal to matrix A, right? If A is Hermitian, then it means these two matrices are same. So if these two matrices are same, this means this element x1 plus iota y1 has to be equal to x1 minus iota y1. So I can write this as x1 plus iota y1, this is equal to x1 minus iota y1. This means x1 will cancel, and from here I will get y1 equals to 0. So this is very important result. In case of Hermitian matrix, this imaginary part of diagonal element, similarly you can show that y4 is also 0. If A is Hermitian, then y1 is 0, y4 is 0. So this means for diagonal elements, you will have purely real elements. Okay, on diagonal, if I have some, you will have only real numbers here. Imaginary part of those complex number will be 0. So this is the first point in case of Hermitian matrix. In case of Hermitian matrix, the diagonal elements are, purely real. Purely real simply means imaginary part is 0. So in case of Hermitian matrix, the diagonal elements will be purely real. This is first point. And the second important point is that, see, this element is x2 plus iota y2. This element is x3 minus iota y3. Now this is nothing but conjugate of this element. And if these two matrices are equal, then it means these two elements has to be equal. So I can say that this element Aij is conjugate of element Aji. So this is second definition of Hermitian matrix. Aij is simply the conjugate of Aji. So this is very, very important definition. Once you know this definition, then you don't have to calculate conjugate transpose of matrix to find whether matrix is Hermitian or not. So if you want to write an example of Hermitian matrix, then first thing you have to write real elements on diagonal. We have seen that in case of Hermitian matrix, the diagonal elements are purely real. So if I have a 3 cross 3 Hermitian matrix, then on diagonal I will have only real elements. So say I have 2, 3 and 4. Now suppose if this element is 2 plus iota, element in first row second column, then element in second row first column, this will be the conjugate of this element. So here I have to write 2 minus iota. Okay, in case of Hermitian matrix, Aij is conjugate of Aji. So A12 is conjugate of A21. Similarly, suppose if I have 3 minus 2 iota here, element in first row third column. So element in third row first column, this will be the conjugate of this element. So here I have to write 3 plus 2 iota. Similarly, suppose here if I have 4 iota, then this element will be conjugate of 4 iota, which is minus 4 iota. So this is an example of a Skew-Hermitian matrix because all the diagonal elements are purely real and Aij is conjugate of Aji. So these two important points you should remember in case of Hermitian matrix. Now the next type is a Skew-Hermitian matrix. Okay, so next is a Skew-Hermitian matrix. So the definition of a Skew-Hermitian matrix is a square matrix A is called a Skew-Hermitian matrix if conjugate transpose of A is minus A. In case of Hermitian matrix, the condition was conjugate transpose of A is matrix A. Now here the definition is conjugate transpose of matrix A is minus A, then in that case the matrix is called a Skew-Hermitian matrix. Now again we are going to see what is the second definition of a Skew-Hermitian, some of the important properties with the help of one example. So suppose our matrix A is x1 plus iota y1, x2 plus iota y2, x3 plus iota y3 and x4 plus iota y4. Only to explain the concept, I am taking an example of 2 cross 2 matrix. So the conjugate transpose of this matrix will be first row will become first column, and we also have to take the conjugate, so we have to change the sign of all these imaginary parts. So this will be our first column. The second column will be x3 minus iota y3, x4 minus iota y4. So this is the conjugate transpose of matrix A. Now if A is a Skew-Hermitian matrix, then this implies conjugate transpose of A is minus A. So this means all these elements are negative of these elements. For example, x1 plus iota y1, this will be negative of x1 minus iota y1. x2 plus iota y2 will be negative of x3 minus iota y3 and so on. So if x1 plus iota y1 is negative of x1 minus iota y1, so this means x1 plus iota y1, this will be minus x1 plus iota y1. These part will cancel. 2x1 is 0, so this means x1 is 0. Now in a similar manner you can show that this x4 is also 0. So this means in case of a Skew-Hermitian matrix, the real part of diagonal element is always 0. x1 is 0, x4 is 0. If you have a 3 cross 3 matrix, then real part of this element is also 0. So this is first point in case of a Skew-Hermitian matrix. In case of a Skew-Hermitian matrix, the diagonal elements are in case of a Skew-Hermitian matrix, the diagonal elements are purely imaginary. Purely imaginary means real part is 0. So purely imaginary or 0. So this is the first point related with a Skew-Hermitian matrix. The real part of diagonal elements of a Skew-Hermitian matrix is always 0. And the second important point is, see, in case of Hermitian matrix, the diagonal elements were purely real, but in case of a Skew-Hermitian matrix, the diagonal elements are either purely imaginary or 0. In Hermitian matrix, imaginary part was 0. Here the real part of diagonal element is 0. And the second important point is, if conjugate transpose of A is negative of A, this means x2 plus iota y2 is negative of x3 minus iota y3. Now this is nothing but conjugate of this element. So this means the second definition of a Skew-Hermitian matrix will be Aij is negative conjugate of Aji. So this is second definition of a Skew-Hermitian matrix. Now if you know this definition, then again you don't have to do any calculation. You can directly tell whether a matrix is a Skew-Hermitian or not. So if I want to write an example of a Skew-Hermitian matrix, then first thing is, on diagonal I have to write purely imaginary elements or 0. So I can write 2 iota here, 0 here, 4 iota here. On diagonal elements, the real part will be always 0. So here for all these three elements, the real part is 0. Now next thing, here if I have 2 plus iota, then this element will be negative conjugate of 2 plus iota. So minus 2 minus iota. Here if I have say 2 plus 3 iota, then this element is in first row and third column. So element in third row first column, this will be negative conjugate of this element 2 plus 3 iota. So conjugate will be 2 minus 3 iota, negative conjugate will be minus 2 minus 3 iota. And similarly, suppose here if I have 6 iota, then this element will be negative conjugate of 6 iota. So this is an example of a Skew-Hermitian matrix. All the diagonal elements are purely imaginary or 0, and Aij is negative conjugate of Aji. So these are two important points related with Skew-Hermitian matrix. The first thing, diagonal elements are always purely imaginary or 0. And the second one is the second definition of a Skew-Hermitian matrix. Okay, so our next type of matrix is unitary matrix. So the definition of this unitary matrix is, a square matrix A is called unitary matrix if A into conjugate transpose of A is identity matrix. If this condition is satisfied, then this matrix A is called unitary matrix. So now again there are two important properties related with unitary matrix. The first one is, determinant of this unitary matrix is either +1 or -1. This is similar to orthogonal matrix. And the second important property is that in case of unitary matrix, A inverse is a conjugate transpose of A. So these two are very, very important property in case of unitary matrix. Now see, these properties are obvious from the orthogonal matrix also. We have discussed at length in orthogonal matrix that if A into B is identity matrix, then it means B is inverse of A, or A is inverse of B. So here also we have two matrices. One matrix is A, another matrix is conjugate transpose of A. And since the product of these two matrices is identity matrix, so therefore second matrix is inverse of first matrix. So conjugate transpose of A is A inverse. So now after learning these 6 matrices, you can relate all these matrices. Symmetric matrix is similar to Hermitian matrix. A Hermitian matrix over the set of real numbers is symmetric matrix. In case of symmetric, the definition was in case of symmetric matrix, the definition was transpose of A is matrix A. In case of Hermitian matrix, the definition was conjugate transpose of matrix A. Conjugate transpose of A is matrix A. So if the matrix is of real number, then this Hermitian matrix is same as symmetric matrix. Similarly, a skew-symmetric and a skew-Hermitian. A skew-symmetric and a skew-Hermitian, these two are similar matrix, meaning that these two are similar in the sense that if the matrix is of real numbers, then in that case a skew-Hermitian matrix will become a skew-symmetric. The reason is that in case of a skew-Hermitian, the definition was conjugate transpose of A is minus A, and in case of skew-symmetric, the definition was transpose of A is matrix A. So symmetric, Hermitian, skew-symmetric, skew-Hermitian, and then the third matrix that we had seen was orthogonal matrix. Now this orthogonal is similar to unitary matrix in the sense that in case of unitary matrix, the definition is A into conjugate transpose of A is identity matrix, and in case of orthogonal matrix, the definition is A into transpose of A is matrix A. So an unitary matrix over the set of real numbers, that will be orthogonal matrix. See why I am talking about the real numbers, because if I have a matrix of real numbers, say if I have this matrix, a very simple example, say 2, 3, 4, 5. If I have this matrix, now here if I ask you what will be the conjugate transpose of this matrix, A to the power theta. So first you have to take the conjugate of each of the element, and then you have to take the transpose. Now since this matrix is of real number, so conjugate will be the same element. Conjugate of 2 is 2, conjugate of 3 is 3, and so on. So conjugate of this matrix A is the same matrix. So basically we have to take the transpose. So this will be 2, 3, 4, 5. So you can see that in case of matrix of real number, conjugate transpose of A is nothing but A transpose. So if the matrix is of real numbers, then conjugate transpose of A, this will become A transpose. And if it is Hermitian, then it has to be symmetric. Similarly, if it is skew-Hermitian, it has to be skew-symmetric. If it is unitary, then it has to be orthogonal matrix. So these are first 6 type of matrices: symmetric, skew-symmetric, orthogonal, Hermitian, skew-Hermitian, unitary. Now after this, we have to talk about the other 4 type of matrices. So the other 4 types are idempotent, nilpotent, involuntary, and periodic matrix. So we'll talk about each one of them. The first one that we are going to discuss is idempotent matrix. So number 7 is idempotent matrix. So the definition of this idempotent matrix is a square matrix. All these matrices are defined only for a square matrix. So a square matrix A is called idempotent matrix. Idempotent matrix if A square is matrix A. If a square of any matrix is the same matrix, then in that case we say that that matrix is idempotent matrix. Now again, there is one very important property related with this idempotent matrix. If A square is A, and if I have to calculate A cube, then I can write A cube as A square into A. Now A square we have seen is A, so I can write this as A into A, which will be A square. This is nothing but matrix A. So if A square is A, meaning that if a matrix is idempotent matrix, then A cube is also A. Similarly, you can show that A to the power 4, this will be A square square. A square is matrix A square is again A. So you can show that A to the power 4 is also matrix A. So in case of idempotent matrix, any power of A to the power n, this will be matrix A. In case of idempotent matrix, so this is very, very important result. In case of idempotent matrix, any positive integral power of A is matrix A. So this was 7th type. Now the number 8 is involuntary matrix. So the definition of this involuntary matrix is a square matrix. A square matrix is called involuntary matrix if A square is identity matrix. So this is the definition of involuntary matrix. If A square is identity, then in that case we say that A is involuntary. If A square is A, then A is idempotent. If A square is identity, then in that case A is involuntary matrix. Now the first point related with this involuntary matrix is that in case of involuntary matrix, the inverse of this matrix A is the same matrix A. And again, this thing is self-explanatory once we know the definition of inverse. Here we have this relation A into A is identity. Now we have seen that if A into B is identity, this implies B is inverse of A. Second matrix is inverse of first, or first is inverse of second. So here we have these two matrices and their product is identity matrix. So this means this second matrix is inverse of first. So in case of involuntary, inverse of the matrix is the same matrix. In case of orthogonal matrix, inverse is the transpose of matrix. In case of involuntary matrix, inverse is the matrix A itself. So this is first property. And the second property is, now see, A square is identity. If I want to calculate A cube, then this A cube will be A square into matrix A. A square is identity, so this will be A. A to the power 4, this will be A square square. A square is identity, identity square is identity. So you can see that odd power of matrix A, if you want to calculate A to the power 5, then you can show this on your own, that A to the power 5, this is also matrix A. This will be A to the power 7, A to the power 9 and so on. So all the odd power of this matrix A will give you A, and all the even power, A square, A to the power 4, A to the power 6, this will give you identity matrix. So this means A to the power n, this has two possible values. Identity if n is even. If n is even number, then A to the power n is identity matrix, and this will be A if n is odd. So this is very important result. In case of idempotent matrix, any positive integral power of A is matrix A. In case of involuntary matrix, A to the power n is either identity or matrix A, depending on whether n is even or odd. So this was number 8. Now we have to talk about the other two type of matrices, periodic matrix and nilpotent matrix. So number 9 is nilpotent matrix. First we'll talk about nilpotent and then we'll see the periodic matrix. So number 9 is nilpotent matrix. Okay, so next concept is nilpotent matrix. Now a square matrix is called nilpotent matrix if A to the power n is null matrix and A to the power n minus 1 is not a null matrix. So this is the definition of nilpotent matrix. If A to the power n is if A to the power n is null matrix and n minus 1 is not a null matrix, then this matrix A is called nilpotent matrix and n is called the index of nilpotent matrix. N is called the index of nilpotent matrix. Now it is important to define the index in this manner, because suppose if I say that, say I have a matrix A, say if I have a matrix A is, and it is given that A is nilpotent matrix, A is nilpotent matrix of index 3. So what is the meaning of this thing? This thing that simply means that suppose if I have matrix A, then calculate A cube and you will find that A cube will be a null matrix, but A square is not null matrix. A square is not null matrix, A is not null matrix, A cube is null matrix. Now the moment this A cube is null matrix, after this all the other powers of A will be null matrix. For example, A to the power 4, this you can write as A cube into A. Now A cube is null matrix, so this will be null matrix into A, which is null matrix. Similarly, you can show that A to the power 5 is also null matrix. So it is important to define the index, because once it is given that index is 3, this means 3, 4, 5, 6, all the other higher power of this matrix A, this will give you null matrix. So that is the meaning of this term index. N minus 1 is not null matrix, but n is null matrix. So this was nilpotent matrix. And the last one is periodic matrix. Now the name this periodic matrix, this is defined from periodic function. The definition of periodic matrix is a square matrix is called periodic matrix. A square matrix is called periodic matrix if A to the power n plus 1 is matrix A. If this condition is satisfied, then the matrix is called periodic matrix and n is called the period of this matrix. N is called the period of this matrix. Now I will explain the meaning of this period with the help of one example. Suppose if it is known that, say, A to the power 4 is matrix A. If it is known that A to the power, it is given that A to the power 4 is matrix A. So what is the meaning of this thing? This simply means that A is a periodic matrix and here the period of this matrix will be 3. right? The condition is a to the power n plus 1 is a, then n is called period. So if I have a to the power 4 equals to a, so this means a is a periodic matrix and period is 3. Now we have to understand the significance of this number 3. So if a to the power 4 is a, then this means a to the power 4 plus 3. A to the power 4 plus 3 means a to the power 7. Now this you can write as a to the power 4 into a to the power 3. Now this information is given. It is given that a to the power 4 is a. So in place of a to the power 4 I can write a. So I will get a into a cube, which is a to the power 4, which is matrix A. So you can see that a to the power 7 is also matrix A. Now similarly a to the power 7 plus 3 10, this you can also show this will be matrix A. You can write 10 as a to the power 7 into a cube. 7 we have already shown as a, so a into a cube, a to the power 4, this will be matrix A. So if I have a periodic matrix of period 3, so you can see that 4 plus 3 is 7, this will give you A. 7 plus 3 10, this will again give you A. 10 plus 3 13, this will again give you A. So that is the meaning of this periodic matrix. After every 3 you are getting the same matrix. A to the power 1 plus 3 is A to the power, then 4 plus 3 is again A, 7 plus 3 A, and so on. So that is the idea behind this periodic matrix. Now this word is taken from the term periodic function. The meaning of periodic function is that if the graph of function repeats itself after a certain interval of time, after a certain interval of x, then we say that that function is periodic function. So for example, we know that sine 2 pi plus x is sin x. So this means sin x is periodic function, and what is the period of this function? Period is 2 pi. So this means the graph of sin x, this will repeat itself after every 2 pi. So we know that this is our graph of y equals to sin x. This point will be 2 pi. Here you will have 4 pi, then you will have 6 pi, and so on. So you can see that the graph between 0 to 2 pi is exactly same as the graph between 2 pi to 4 pi, 4 pi to 6 pi, and so on. So this periodic matrix is also derived from, the name periodic matrix is also derived from here, that after every 3 you are getting the same matrix, and therefore this A is periodic matrix. So this was 10 basic type of matrices. Now after this we'll take some problems based on the different type of matrices that we have seen. Okay, so now our next two problems are, the first question is, these two problems are based on idempotent matrix. The first question is, if AB is A and BA is B, then we have to show that both A and B are idempotent matrix. So we have seen that in case of idempotent matrix, the definition was if A square is A, then this implies A is idempotent matrix. A is idempotent matrix if A square is A. So now we have to show that these two matrices A and B are satisfying these conditions. Now the information that is given is A into B is matrix A and B into A is matrix B. This information is given. So if I can show that A square is A, then it means A is idempotent matrix. So see, I can write this A square as, A is nothing but AB. So I can write A square as AB square. Now this AB square will mean AB into AB. Now in place of this BA, we can write B. In place of AB you can write A, and in place of BA you can write B. So now this will become A. In place of BA we can write B. Now in place of this AB we can write A. So finally this AB will become A. So as you can see that this A square is A, and this means A is idempotent. If A square is matrix A, then it means matrix A is idempotent matrix. The second one is we have to show that B is also idempotent matrix. So this means we have to show that B square is equal to B. So in place of B square, B is nothing but BA. So in place of B square, we can write BA square. Now this will be BA into BA. In place of AB, we can write A. And in place of BA, you can write B. And finally this B into A, this will become B. So as you can see that this B square is equal to B, and this means B is idempotent matrix. So in this way you can show that both A and B are idempotent matrix. Now the next problem that we have is, if A is idempotent matrix and A plus B is identity matrix, then show that B is also idempotent matrix. So here also we have to apply the same approach. We have to prove that B square is equal to matrix B. Now it is given that A is idempotent. So this means A square is matrix A. This information is given. And we have to show that B square is equal to B. Now from this relation A plus B, this equals to identity matrix. I can write that B is nothing but identity minus A. Now we have to show that B square is equal to A. So B square, this will be nothing but identity minus A square. So this will be, now since A and I, these two are commutative matrix, this we have seen in our earlier discussion. So here we can apply the formula of A minus B square. So I can write this as identity square plus A square minus 2 times A into identity. Now in place of A square we can write matrix A because it is given that A is idempotent. Identity square is identity, so identity plus A minus 2A. So this will be identity minus A. Identity minus A is nothing but matrix B. So as you can see that we have shown that B square is matrix B, and this implies that B is idempotent matrix. So these two were very simple problem. Only thing is that you have to know the definition of this idempotent matrix. So a square matrix is idempotent if A square is A. Now after this we'll talk, so these were the two basic problems on idempotent matrix.